days, or even weeks later, as the fault plane settles down to its new position. In 1992, an earthquake in California damaged the telescope in this observatory.
Holy cow! Holy cow! Oh my God!
But this video isn't the main tremor. It's an aftershock. It was taped on the day after the quake by a member of the staff.
Larger earthquake.
He'd returned with a camera to survey the damage. As he taped, the aftershock struck.
I'm okay! Oh my God. All right. I'm on my way out. Stand by. I'm on my way out.
Hey, come on. Where are you?
Top floor.
What happened here? Out here. What happened to the top floor?
Destroyed.
What do you
Go, go, go. Come on. It may fall off. Go.
Get it, man.
Come. I got it on tape.
Right.
I got it on tape.
The aftershock tore up the causeway that linked the observatory to the lake shore. And like the quake that struck Italy in 1997, caused more damage than the original quake. So, what can we do to protect ourselves from earthquakes and the dreadful damage they cause? The obvious answer is for science to find methods of predicting tremors. The problem is that large earthquakes don't happen very often. 10 to 20 minor earthquakes occur in the ground beneath San Francisco every day. But until 1989, there hadn't been a major tremor since the famous earthquake of 1906. So how can science distinguish between the causes of thousands of small tremors and the one big one which can destroy a city?
Earthquakes are probably fundamentally unpredictable. And a key to seeing why that's true is to understand that we don't really want to predict earthquakes. There are 20 or 30 earthquakes every day somewhere in Southern California, just Southern California. What we're trying to do is not to predict earthquakes, but to predict which of the earthquakes we have are going to turn out to be large ones. To be able to do that, there would have to be something different in the way a big earthquake begins than in the way a small earthquake begins. And as far as we can tell, there isn't a difference.
If we're ever going to predict earthquakes, we must be able to measure changes in the earth, which indicate they're about to happen. For scientists, that means collecting and analyzing data before the tremor. And that means getting instruments in advance to a site where one will occur. That's why the tiny community of Parkfield in Central California became the focus of scientific attention in the mid-1980s. Parkfield lies on the San Andreas Fault, and for over a century, a moderate earthquake had occurred there roughly every 22 years. The next one was due before 1993. So the U.S. Geological Survey installed millions of dollars worth of equipment into the Parkfield area. They drilled holes for deep seismographs, installed lasers to measure tiny movements in the land, and video cameras to record the event. Any change in the ground, the tiniest buildup of strain or tilt could be measured. And then they waited and waited. 1993 came and went. Several years later, the earthquake still had not occurred. This is the problem with trying to predict earthquakes. We may, from past evidence, be able to forecast when one should occur, but that doesn't mean that it will. Tokyo has a major quake every 60 to 70 years. The last great earthquake there was in 1923. 143,000 people died. The next big one is now overdue. But there is simply no reliable way of predicting precisely when it will happen. All we can say is that a large quake will almost certainly occur there sometime in the next few years. There are many methods which claim to give warning of an impending earthquake, but for every tremor which does give some advance warning, there are hundreds of others which occur without any early signs at all.
How big an earthquake is depends not on how it starts, but on how it stops. Because the bigger the fault is, the bigger your area is. So if you start here and travel just 10 meters, it's a magnitude 4. You start here and travel 100 kilometers, it's going to be a magnitude 7. And how it stops may have nothing to do with how it starts. And if that's true, we'll never predict them.
We cannot predict earthquakes. All we can do is be prepared for them. Japan has invested heavily in learning centers designed to show what it's like to live through one. Each day, groups of office workers, children, and housewives come here to feel what it's like and to practice the routines they should go through in a real quake. But they're not told that in a large earthquake, their kitchens may just disappear. Some centers even have smoke chambers, where people can experience trying to escape from a smoke-filled house. But this smoke isn't choking and poisonous, and it's not in the middle of a blazing inferno. And there are simulators which mimic actual earthquakes. This one is reproducing the violent shaking of the Kobe earthquake. It's a useful reminder of what to expect, but in a real earthquake, there will be no warning, no time to brace themselves. Once a year, most towns and cities in Japan hold an Earthquake Preparedness Day. Everyone has a role. The Japanese take the annual drill very seriously. But would this ordered exercise be useful in the face of the sudden chaos of a real tremor? If the roads are blocked, water mains shattered, hospitals destroyed, all this preparation might seem futile. The Kobe earthquake caught everyone by surprise. And before the authorities took control, there were several days of complete chaos. These are hard questions for the government to answer, but psychologically, these exercises are important for the people living in the most earthquake-prone country on Earth, to help them feel they are at least preparing themselves. Another challenge is to make buildings and structures safe so they don't collapse. Engineers and architects now use large shaking tables which reproduce precisely the ground movement of powerful earthquakes. Different methods of reinforcing can be tested to see which work best. Some modern buildings now rest on floating bases, which absorb the energy of a tremor. Others, especially very tall buildings, use electrically driven counterweights at the top, which rock in the opposite direction to the shaking. The model building on the left is unprotected, while the one on the right has this system. It works, but it's extremely expensive. Even if the building survives, an earthquake can cause immense destruction to what's inside. In the 1994 Northridge quake, over half the $30 billion repair bill came from damage to the contents. One company in Los Angeles has developed methods for securing the entire contents of any building in the event of an earthquake.
This is a typical angle iron, an L bracket. It's very rigid, and during a severe or moderate earthquake, it can actually pull away from the wall or rip the piece of furniture. The state-of-the-art version is this flex bracket, and it's designed to do just that. That is, flex with the motion of an earthquake.
They have devised a simple but powerful demonstration of the need to secure contents, shaking a room just as it would be in a moderate quake. Then they rebuild the room, securing all the contents.
What you're seeing behind me is a demonstration of a 6.5 magnitude earthquake. The bookcase, the computer table, the table itself, the pictures, the file cabinet, and the cabinet doors have all been secured to mitigate loss or injury. This can apply to homes, hospitals, businesses, anyone who lives in an earthquake zone.
Modern technology has given us a new method of preparing for earthquakes, the early warning system. Shock waves from a tremor travel through rock at about 2 miles a second. Seismic detectors, linked by radio and computer, can register the shock and flash a warning instantly. This could give a city 50 miles away at least 20 seconds warning that an earthquake is about to hit. This may not seem much, but it can be a lifesaver. In the aftermath of an earthquake 100 miles from Mexico City in 1994, rescuers carried pagers linked to the seismographs. When aftershocks occurred, they had almost a minute to get clear of dangerous buildings before the shock actually hit. There were less obvious applications. In the 1989 Loma Prieta quake, some fire engines were unable to get out of their stations because the quake buckled the doors and they couldn't be opened. So now, at the headquarters of the San Francisco Emergency Services, they're using new technology. When an earthquake starts, a special seismograph picks up the first shock wave. It instantly sends out signals, which sound the alarms and automatically open the doors of all the local fire stations before anyone even knows an earthquake is on its way.
Everybody, everybody!
Let's go.
Everybody, everybody!
By the time the quake hits, the doors are already open and the fire crews are moving. This early warning network is growing all the time. The Bay Area Rapid Transit, San Francisco's underground train system, now has seismic alarms to warn the control staff. They can then automatically shut down the system if necessary. Although in the Loma Prieta earthquake, there was no danger at all to the network. Underground in a train was one of the safest places to be. Within the next few years, many other organizations will have these systems: hospitals, offices, schools. All these and many others could benefit from just a few seconds warning that an earthquake is about to strike. Earthquakes have always been with us, and they always will be. As long as we continue to live in parts of the world where they are a threat, towns and cities will be damaged and destroyed. People will be killed and injured. We can't prevent earthquakes. We know where they are most likely to occur, but we can't predict when they will strike. Living with earthquakes is living with risk. We are truly at the mercy of our raging planet.